Today we're going to talk about the polarity of bonds and therefore the polarity of molecules. Bond polarity happens when we have two atoms that have very different electronegativity values. Those different electronegativity values cause the electrons that are present in those electron clouds to be shared unequally between those two atoms. Now remember, it's sometimes referred to electronegativity as the tug of war force between those atoms as the nucleus is attracting those electrons towards it and that are being shared. So that shared pair of electrons is, I guess you can say, being fought over by the two atoms. And depending on whose electronegativity is higher will determine where the electrons are going to spend the majority of their time. Now, there are tables that will give you electronegativity values for the different elements. I'm going to show you one here. I'm not going to flip back and forth to it. You should have access to this in your notes. But these electronegativity values here just show you a relative strength that these elements have for the electrons that are shared in a bond between the atoms. The first example we're going to look at on the notes is the bond between hydrogen and fluorine. And so if you look at hydrogen here, hydrogen has an electronegativity value of 2.20. Fluorine has an electronegativity value of 3.98. So those are the values that we're going to be looking at here. So 2.20 for hydrogen, 3.98 for fluorine. That means fluorine's got a stronger pull on the electrons. And if you'll notice, what this diagram is trying to represent is that the electrons are spending more time in the vicinity of the fluorine nucleus than they are around the hydrogen nucleus. What that does is create a partial negative charge over here with fluorine. Now I've drawn it here, but handwritten, it looks kind of like an almost completed 8. So there's a partial negative, that's a partial symbol, partial negative over here, not a full-fledged negative charge. The only way you get a full negative would be if fluorine completely stole the electron away from hydrogen. It's not strong enough to do that, but it is strong enough to keep way more than its fair share of the electron pair over in its vicinity. Hydrogen, on the other hand, gets a partial positive charge, and what that sets up is a dipole. A dipole meaning it's got two poles, positive and negative, and that is referred to as a polar bond. Now, the way we often represent that is to show instead of showing just a dash between the hydrogen and fluorine, we show an arrow, and we're going to put a little slash through the arrow to show that this is not a chemical reaction. We're not turning hydrogen into fluorine, but what we are showing is that the bond between hydrogen and fluorine is a polar bond, and that the majority of the time the electrons are in the region or vicinity of fluorine's nucleus. So that would be an electron or Lewis dot structure for hydrogen fluoride, HF, if we were going to emphasize the polarity of the bond. Molecules also can be polar or nonpolar depending on their structure. Water, for instance, if you look at water structure down here, water has the two hydrogens attached to the oxygen here. And if you look up the electronegativity values of hydrogen and oxygen, and we'll do this one more time, looking up the electronegativity values. We already know that hydrogen is 2.2. Oxygen, on the other hand, if you'll look up here, is 3.44. So oxygen has the higher electronegativity value. So we're going to show those bonds pointing in towards oxygen. So oxygen is pulling electrons towards it more. And you'll also notice that over here we have two lone pairs in this vicinity on oxygen. So we've got this big, huge electron density over there in oxygen's area. So that's going to give down here on this end, a partial negative charge for the water molecule, and up here a partial positive for the hydrogen end of the water molecule. So we're going to talk way more about the polarity of water and how that affects many different areas in chemistry later. Right now we're just pointing out that this is going to be a polar molecule. It has an uneven distribution of charge. It is not symmetrical. It's an uneven distribution of charge. So we've got a positive and a negative end on the molecule. Now, take for instance carbon tetrachloride. If we have carbon tetrachloride with carbon in the middle and the chlorines around it symmetrically, that is an even distribution of charge. An even distribution of charge, meaning that yes, they are all polar bonds. If we look at the electronegativity values of carbon and chlorine, you'll notice that chlorine is a more electronegative element, and that is going to create polar bonds. But remember, it's about whether that molecule has positive and negative regions around it, and it does not. It is symmetrically arranged around that central atom, and therefore the charge distribution is very even and symmetrical, so there's no polarity there for the molecule itself. In general, molecules are non-polar if there are no lone pairs on the central atom. That's one way you can look at it. It's not 100%. We'll see some exceptions to the rule for that later. But in general, if there are no lone pairs on the central atom and all of the peripheral atoms, for instance, in the example we had above, the peripheral atoms would have been chlorine. They're the atoms that are surrounding the central atom. If all of those are the same, then we're going to have a non-polar molecule. As soon as we do something like this, where we have chlorines in every position, except maybe a fluorine down here, now it's no longer symmetrical, and it becomes a polar molecule. So it has to have no lone pairs, and all peripheral atoms are the same. Now on your assignment, what you're going to be looking at is determining whether bonds between two elements are going to be polar or not. And there's a range of electronegativity difference. You're simply going to look up the electronegativity value for each of the elements, and you're going to subtract, find the difference between them. And based on the difference range, you're going to be able to tell whether it's going to be classified as non-polar covalent. It has no polarity. Moderately polar covalent. You've got 0.4 up to 0.99 difference for moderately polar covalent. Highly polar covalent from 1 to 1.99, and then if it's greater than or equal to 2, we're going to consider that strong enough to rip the electron away. Now we're not talking about still sharing. We're not talking about somebody getting more than its fair share, but the other element hanging on for dear life. In this case, you would have a complete transfer of electrons, and it would not even be a covalent bond anymore. It would be ionic. So let's look at these examples. This is what I want you to do. On HF, we've already looked at that one. We saw that hydrogen was 2.20 and fluorine is 3.98. Sodium is 0.93. I'm just going to look all of these up at one time, and you can go to the electronegativity chart and look these up. 3.16 for chlorine. You're just going to look up those electronegativity values, and then you're going to subtract them. If you subtract HF from 3.98 minus 2.20, you're going to get 1.78. Now look in our chart up above. This says that if you have a 1.78 value for the electronegativity difference, that you're going to have a highly polar covalent bond. If you subtract 3.16 and 0.93, you end up with 2.23. Notice that in this case, We have something that is such a large electronegativity difference that we're actually going to be able to have chlorine strip the electron away from sodium. So it's not even going to be a covalent bond anymore. It's going to be an ionic bond. So this is an ionic bond, a complete transfer of electrons. Bromine, as far as I'm concerned, if it's a diatomic element, you don't even have to look up the electronegativity, because if you think about it, they're both going to be the same. And if they're both the same electronegativity value, then obviously their difference is going to be zero. And if we have a zero electronegativity difference, then that is our nonpolar covalent bond. And finally, for nitrogen and oxygen, nitrogen is 3.04, oxygen is 3.44. This gives us an electronegativity difference when we subtract of 0.40, and if you look up in our chart, you will see that that is the moderately polar covalent range.